Uh, this recording is going to be the practice final for fall semester. And I'm just going to, on this recording, I'm just going to do the first 13 problems. So this will be part 1 of the practice final, and then there will be a second recording that will include questions 14 to 26. Okay, so starting with number 1. Number 1 is a density problem, and it says that copper has a density of 8.93 grams per milliliter. So grams over milliliters. And it says if a copper statue has a volume of 1.40 liters, then what is its mass? Okay, so we know the formula for density is equal to mass divided by volume. So to solve for mass, we'll multiply both sides by V. So then volume times density is going to give us the mass. The other thing that you should notice here is that density is in milliliters and volume is in liters. So we need to get that volume converted to milliliters. So 1,000 milliliters in a liter. So the liters cancel. So the volume is going to be equal to 1,400 milliliters. And in terms of significant figures, since we need 3 significant figures, we need to write this as 1.40 times 10 cubed milliliters. Okay, now we're ready to just plug in the numbers. So the volume is 1.40 times 10 cubed milliliters. And the density was 8.93 grams over milliliters. So milliliters on the top and bottom will cancel. And what we will get for mass then is 12,502 grams. And we want 3 significant figures, and therefore our answer would be 12,500 grams. Okay, number 2 is a unit conversion problem. On a basketball court, the distance from the free throw line to the backboard is 4.57 meters. How many centimeters is that? What is the distance in centimeters? So we're moving from meters to centimeters, so centimeters goes on top, and there are 100 centimeters in a meter. Okay, so meters cancel, and your answer then is 457 centimeters. Okay, number 3 has parts A, B, and C, and what you're asked to do there is to indicate the number of significant figures. So for this one, every one of those digits is significant, so it's 5. This 0 is significant because it's to the right of the decimal place and is at the end. this 0 is significant because it's between two non-zeros, and so those obviously are significant. So all 5 are significant. The next one is 0.00390. These two zeros are not significant. They're to the right of the decimal place, but they're not at the end. So they are not significant. This one is significant because it's to the right of the decimal place and at the end. So that has 3 significant figures. And then 8.20 times 10 squared. That one would have 3 significant figures. The 2 non-zeros are significant. This is significant because it's to the right of the decimal place and at the end, so that's 3 significant figures for that one. Okay, number 4 is converting to scientific notation. So 42,803,000. So first of all, this number has 5 significant figures. So the zeros on the end are not significant, but the other digits are. So we need to keep those 5 significant figures. So it's going to be 4.2803 times 10 to the, so how many places do we need to move the decimal place to get from here to the 4.2? So 1, 2, 3, 4, 5, 6, 7. So it would be times 10 to the 7. 4.2803 times 10 to the 7. And then part B is 0, 0, 0, 0, 0, 8, 4, 3. So again, looking at significant figures, none of those zeros are significant. They're to the right of the decimal place, but they're not at the end. So we have 3 significant figures. So it would be 8.43 times 10 to the, so now we're moving the decimal place to the right, so it's going to be a negative exponent. So we're moving it 1, 2, 3, 4, 5, 6 places. So it's 10 to the negative 6. 8.43 times 10 to the negative 6. Okay, question number 5 asks which of the following are isotopes? And the answer to that would be A and D would be isotopes of each other. And the reason is that they both have 20 protons and they both have 20 electrons, but they have different numbers of neutrons. So A has 21 neutrons and D has 20 neutrons. So isotopes are those atoms that have the same number of protons but different numbers of neutrons. And that atom would actually be calcium. So in terms of how we would write these isotopes, we would take, for this one, you would take the protons plus the neutrons. So this would be calcium 41 is A. And then for D, it would be calcium 40 because it's the protons plus the neutrons. And these also, remember, can be written like this. Okay, that's the same thing. It's just a different way of writing isotopes. Okay, so again, this number is protons plus neutrons. And if it has 20 protons, then we know that it's calcium. Okay, number 6. What is the frequency of light that has a wavelength? So wavelength is equal to 10.0 nanometers. Okay, so the formula for frequency is the speed of light divided by wavelength. So you'll be given the speed of light is 3.0 times 10 to the 8 meters per second. And then you're given the wavelength as 10.0 nanometers. However, since the speed of light is in meters, we need to change this to meters. And what you will be given is that 1 nanometer is equal to 10 to the negative 9 meters. So however many nanometers, you just raise that to the 10 to the negative 9th power. So this is going to be 10.0 times 10 to the 9th meters. Okay, so you have meters, meters divided by meters is 1. So that's 1 over seconds, which is a hertz. So your units are going to be hertz. And if we 3.0 times 10 to the 8th divided by 10.0 times 10 to the negative 9. Sorry, I forgot to put the negative 9 in there. That will equal 3.0 times 10 to the 16 hertz. And actually, it looks like I guess we need to have 3 significant figures because of this. So we would actually say 3.00 times 10 to the 16, 1 over second, 1 per second, or hertz. Okay, number 7 gives us an electron configuration and asks what is wrong with it. So we'll write this out. Okay, so sorry, I1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Okay, so then it asks us what is wrong with this, and you should recognize that an s orbital can only hold 2 electrons, so this needs to be 2s2. So if we correct this then and make that a 2s2, then you should be able to figure out what that element is. So 1s2, we're in 4s2, and then 3d6 or 3d5. This would be manganese. And manganese, if you add up all these electrons, you're going to get 25. And if you look on the periodic chart, manganese is number 25. So it has 25 protons, and therefore it has 25 electrons. Okay, number 9, or no, I'm sorry, number 8. Give the full electron configuration for NB. So NB is in the 5th row, and it's the 5th one over. So we'll just start with 1s2, 2s2, 2p6. 3s2, 3p6, 4s2. Okay, now once we get to row 4, then we have the D level, but we drop that down an energy level, so it'll be 3D10, and then 4P6, then 5S2, and then go to the D, so we're going to drop back 1, and to get over to NB, we'll go over only 3, so it would be 4D3. Okay, then number 9 asks us for the abbreviated electron configuration for FR. So FR is francium, and it's number 87 on the periodic chart, and it's in row 7. So what you need to do then is drop back to row 6, column 8, which is RN, put that in brackets, and then you just pick up with the next row for the electron configuration. So it would be 7s1. Okay, number 10. What is the chemical formula and name of the compound that is formed by magnesium and phosphorus? Okay, so magnesium is Mg, phosphorus is P. So the first thing you have to ask yourself is that ionic or covalent, and it's ionic. Magnesium is a metal. Phosphorus is a non-metal. So we need to figure out what the charges are. Magnesium is in group 2A, so it will give up 2 electrons, so it will have a positive 2 charge. Phosphorus is in group 5A, so it will gain 3 electrons, and so its charge will be -3. And then in writing the chemical formula, we switch the charges. So it'll be Mg3P2. And for naming ionic compounds, we just name the first element, so magnesium. And then for the second one, we just put the ending "ide" on it. So it would be magnesium phosphide. And number 11. Determine the Lewis structure for NF3. Okay, so nitrogen has 5, it's in group 5A, so it has 5 valence electrons. So it's going to have 3 electrons that are not paired. And then there's 3 fluorines, and each of those fluorines is going to have 7 valence electrons. So each of the 3 fluorines will have 1 unpaired electron. Okay, so you should be starting to see then that we can take those unpaired electrons on the fluorines and pair them with the unpaired electron on the nitrogen. Okay, so we'll take this one and they'll share that unpaired electron. We'll take this one, this unpaired electron will share here. And then this one, the unpaired electron will share with this one. So we'll erase these since we moved them. And then remember to put the paired electrons that are present on that fluorine. So now, with the sharing of electrons, the nitrogen and all three of the fluorines have their 8 valence electrons. Okay, so then you're asked to draw the stick figure. So the central atom is going to be the nitrogen because it has the most, the highest number of unpaired electrons. And it has, of the 4 spots around it, it has 1 pair of unpaired electrons. And therefore, the shape is going to be pyramid. And we would picture that then as, this is how we draw a pyramid shape. And then the dotted line this way. Okay, so each of the 3 fluorines. If you want to show which one is most electronegative, you draw the arrow toward the fluorine because it's farther to the right and higher than the nitrogen. It's actually just farther to the right. They're both in the same row, but the fluorine is further to the right. And because you're not getting, because of these 2 unpaired electrons on the nitrogen, you're not going to get pull in all directions on that nitrogen, so that's going to make this a polar molecule. And polar molecules do dissolve in water. That's a little bit of extra information that you weren't asked for that question, but it's good to think about that. And if there's not equal pull on all sides of the central atom, you're going to end up with a charge within the atom that makes it polar. And polar molecules dissolve in water. Non-polar molecules do not. Okay, number 12 is 4 parts to name the following compounds. So 12A is Al2, S3. Okay, so when you look at that, first of all, you should recognize that it's ionic. And so the way that we name ionic compounds, name the first element, and the second one gets the ending "ide." So aluminum sulfide. Okay, B is SF2. Okay, this is covalent. It's 2 nonmetals, and so we'll name the first one sulfur. And then the second one is going to get the prefix di with the ending fluoride. So we don't say monosulfur. If there's only one of the first atom, we don't put the prefix mono on it. If there were just one sulfur, one fluoride, if the second one, if there's just one of those, we would put the mono on, but not for the first atom, the first element. Okay, then we have C2F6. So again, this is covalent, 2 nonmetals. So this would be dicarbon. And then for 6, it's hexafluoride. And then D is BeF2. Okay, so that's ionic. Beryllium is a metal, fluorine is a nonmetal. So we would name it beryllium and then the ending "ide" for the fluoride. Okay, number 13. Which of the following, so we have carbon, nitrogen, fluorine, which of those are homonuclear diatomics? And the answers are nitrogen and fluorine. So if they exist by themselves, not bound to anything except themselves, then they would always be written as a 2. N2, nitrogen gas, fluorine gas, F2. Okay, so we'll stop there. That's halfway through the practice test. And the next video will do the remaining part of it.